there, fellow 3D printing enthusiasts all around the world. We are delighted to have you as our guests today. My name is Daniel Ploss. I'm responsible for the business development for our additive manufacturing products here in HxGN. I was the former sales director at CATS Additive, and since the acquisition from last year, I'm part of this interesting and wonderful team. Today, we show you a unique solution on the market that combines simplicity and function. The presenter of this solution is Peter Leitner. He's our senior product engineer and will walk with you through the process of data preparation to show the simulation, how it works and what you can simulate in the solution. As you know, we have 3 suites at the moment in HxGN, and one of them, the new one, is our AM additive manufacturing suite with several products. And in the first webinar we had 3 weeks ago, we focused on AM Studio, so our data prep solution for powder bed fusion printers. On the second seminar, we watched to the whole process chain, beginning from CAD, from the designer, through AM Studio to Esprit, also the post-processing, and showcase the whole procedure. And today, the main focus is the power of process simulation powered on SimFact. And we show you the subset from SimFact in AM Studio. So we brought the main functionalities for a first flavor to AM Studio. On AM Studio, we are starting with the preparation for manufacturing. Then we do all the build preparation for the machining, the programming, and then usually in step 4 here in our a circle of the process chain, we do the process simulation and optimization with SimFact. But now in our scenario, we have these functionalities embedded in AM Studio. And so the big advantage for you is if you make changes on the geometry around the supports, then it's very easy to stay in the same environment, and you do not have to switch to other products and can do everything in one solution. SimFact is the big solution in HxGN for the process simulation, which offering quite a lot of functions, much more than we have a subset in AM Studio. But our main function is the distortion prediction and compensation, and also the support structure optimization. So we will walk through these procedures today with you to show you exactly how these points can help during the procedure of data preparation. Here again, another view for the workflow, what we do with AM Studio and where the process simulation is based in this process chain. So we start with the import with native or STL files. We repair these files, then it comes to find the right orientation. We support the part, and then usually in the procedure or in the printer itself, it leads to strains and forces in the part. And to prevent that, we do the process simulation. In that step, you see here after the support, and then yes, you can really check if the support is stiff enough, or if the geometry will maybe have a distortion somewhere, and you can make a pre-deformation. And then you can go to the philosophy of first time right printing and save a lot of money, because you do not need to have 2 or 3 tries till you can ship your part. And then it comes to slicing and hatching and convert the internal file to the printer itself. And the very nice thing is in AM Studio, beside all the USPs we have, the process simulation is an integrated part, and it's delivered as a standard when you install AM Studio. It's limited to 1 core, but anyway, you can start your first tries with process simulation. And if you recognize the power, then either you can upgrade it in EM Studio, or you can switch to the full version to the SimUFACT agnostic tool. A small overview about our partners, which we address directly with EM Studio. So all the big players on the market. Probably you know the most of them. And if you, for instance, have some new players or you work with new players on the market, we will help you to integrate this printer OEMs as well to EM Studio. Just give me a call. I will support you in all matters regarding the sales procedure or demo installations with EM Studio to understand how it will work for you. A small overview from our customers from all around the world. So mostly in automotive or dental or some other universities, but also quite a lot solutions from all the other industries like aerospace and defense. In the end, a small event tip for June. So we will show on HxGN vans how this solution is really working on a customer project. So you can sign on to Hexagon Live Virtual Manufacturing in June and see exactly on a customer project how it's working, the embedded solution in EM Studio with SimUFACT. And now it's part for the live demo. I like to hand over to Peter, and afterwards we can start the discussion and Q&A communication. Thank you from my side so far.
Thank you. I will share my screen as well. So a warm welcome from my side as well. I hope you can see my screen now. I simply started EM Studio and I will start a LaserTech 30 SLM machine from DMG Mori for the demo today. I'll start with a pretty easy part. It's a tube-like or pipe-like structure that I want to show you the aim of the simulation inside EM Studio. I checked the part, so there are some smaller errors. I can automatically heal them, and I want to leave the part in the orientation as it is for a better representation or for better visualization of the simulation approach. I have to position some supports underneath, therefore I want to use the adaptive cells, which were described in the first webinar, I think 3 weeks ago, around about that. Exactly. And then I want to jump over to the main point of our presentation today. It's the process simulation, and you can find the process simulation in step 5 of our workflow, build process. And first thing that you have to do is you have to define a voxel size. And with this voxel size, the user can treat the accuracy of the simulation results and the simulation runtime. So a smaller voxel size indicates more voxels which will be generated and will end up in a longer calculation time, but a more accurate result. So as it can be mentioned here, I have now generated the voxels, and you can see different colors here. The darker violet one indicate they have more volume fraction than the lighter violet one. And what you can also see here is that not all the geometry is fully voxeled. There's a parameter, the 5% fraction of part parameter, which you can increase or decrease if you are not happy with that. But you can also see here after the voxelizing a short summary of how many voxels how many voxels are generated and how many simulation layers are necessary to run the simulation in an accurate way. What you can see here as well is that I use 4 cores. As Daniel mentioned beforehand, in the standard version, you have the possibility of 1 core, but you can increase the number of cores within a license model. So you can use up to 4 cores. The simulation is finished in the meantime, and you can see the results. So here on the right-hand side, you can see a legend. You can adapt the legend in a way, for example, from 0 to 0.3 millimeters. You can scale the displacement, so you can get a better feeling of how the deformation is acting, in which direction, and so on. And you can see a slider between the voxel result, the voxeling, the results on voxel level, and the results on mesh level. I will go into that in details later on. So what you can see here is that there are 2 red hotspots on this tube. So there is this one, and here on the bottom as well. And one main benefit of simulation inside the data preparation is that we can now act onto the results. So I can jump back to the supports. There were some areas which were red, or where there was a lot of deformation, and what I missed beforehand was to support these line support regions. And I want to add here a block support with a line thickening of 1 millimeter. So in left and right side, there are block support structures generated underneath. And again, jumping back to the step 5, I can now rerun the simulation based upon the new setup, based upon the new supports that I have generated, and I get mentioned that the old results will be removed. So we have to remove the old results before we start the new simulation. Again, I run a very rough simulation with a voxel size of 2 millimeters, only to have a quick run time. And for a sort of a sanity check that we are now running, I want to find out if there are any critical areas, and for that I do not have to make a very small voxel size, because what I mentioned beforehand, the simulation time will increase immensely when you decrease the voxel size. And what you can see here now, this big red area, which was beforehand in the first simulation here visualized, now got back to a more orange one, but the hotspot here on the upper circle still remains. So again, we can visualize this one, and this is very physical, that the deformation will look like that, because you have the spherical or elliptical scan area, and due to that fact, it will bend a bit into the middle here. So what we can do is we can use the deformation or the pre-deformation for that to get aware of, or to get an accurate path out of it. But therefore, first I want to decrease the voxel size a bit to get a more accurate simulation result out of it. It's still not ours, to be honest, but what you can see here is that the voxel, the number of voxels simply doubles from, I think it was 10,000 voxels in the first simulation, and now we have 90,000 voxels, which directly influences the simulation time. But as I mentioned, the simulation results will also get better by having more voxels available. It takes about a minute to run this simulation. But what I want to show you here is how we can now calibrate the simulation to a real print job result. And No, will be finished soon. What you can see here as well is that the simulation time, or the progress here on the bottom, is at the beginning very fast, and then it gets slower and slower. I will describe that later on as well. Yeah, now that the new results are visualized, I can switch back to automatical scaling here. And what I want to do first is I want to set a deformation value of 1. What does that mean? A deformation value of 1 means I want to deform the part in a way so that the part, or the mesh that is visualized here, represents the part when I print the part as it is. And now I want to measure the diameter of this tube structure. This should be 36 millimeters, and it will be after printing, after the simulation predicts a diameter of 35.34, around about that. And what I have done is I really printed that part, and I simply measured the diameter with a measurement slide, and I found out that the diameter is not 35.3 or 4, it's 35.6. So that indicates that the structure is too weak. It bends more to the middle than it bends in the reality. And what I can do there is I can change the inherent strain values here. This is more or less the basic of the simulation, or for this very fast simulation, it's the inherent strains are more or less the basis for the calculation. And due to the fact that it was too weak, I have to decrease the strain value so that less stresses will be the result. So I will go with a value of 0.02. Beforehand it was 0.035. Save it, and jumping back again to the simulation, and again I can run a simulation which will again take about a minute. But what I mentioned before, you can see that the simulation process is very fast at the beginning and gets slower the more to the end it comes. The reason for that is the simulation gets slower because the continuum which has to be used for the simulation is getting more and more complex the higher the simulation is, and that's the reason why it starts very fast and gets slower to the end of the process bar here on the bottom. Again, we are nearly finished, and what we hope is that we now can find a diameter of 35.6, around about that, because we adapted the inherent strains. Again, I have to deform the part, and again I want to measure the diameter here, like I will do it with the measurement slide. And what you can see here, I exactly found the 35.6 millimeters. So now my simulation and my real print job are calibrated to each other. And now it brings me to the point of pre-deformation. I now can pre-deform the part in a way so that the printed part will be the accurate part with a diameter of 36 millimeters. So what I will do now, I simply counter deform the part in the opposite direction. So what you can see in this infographic, the deformed part is the blue one. It's the more or less the printed or the simulation result. Then I counter deform this simulation result to the pre-deformed model, and I will end up with an accurate part. And the nice thing about that is when I hit apply, all the supports immediately will be regenerated based upon the new geometry, because we are doing slight adaptations on the mesh, and so the supports have to be regenerated, so everything fits to the real world. Let's call it this way. And then I'm done. I can jump over to a build process. I can assign the slicing and hatching profiles and run this. I can generate the SLM file or the machine file. And what I have done in the past is I printed those parts 8 times on a base plate. The right 4 were printed as they are, no pre-deformation done on them. And what you can see here again, we will find all of the results in a range of 35.6 millimeters, round about that, independent from the orientation and the position of the part on the base plate. And on the left-hand side, we find the pre-deformed parts. So I have done the same approach that I have shown you beforehand. I counter-deformed the part, and then I printed the counter-deformed parts. And I ended up with a diameter of 36.0, 0.04, 0.02, 0.09. So I ended up with an accurate part. And these are the 2 main aims that I wanted to show you in the first step. You can do a sort of a sanity check. So I can find out regions where I need to add more supports, or where I have possibly missed to set the support underneath. And on the other hand, I can use the pre-deformation to get aware of the deformations of the part by simply pre-deforming the part. So that's the first approach that I wanted to show you here. So I can calibrate the simulation based on a printing result, on a real printed part. But when I want to use the pre-deformation without having printed the part, so we're speaking here about first-time right parts, then there is another approach, and therefore we have to jump into the machine settings. And there is a step which is called simulation calibration. And for that, there's a description what that means. And nearly the same approach that we have done now manually can be automatically done by the simulation, or by AM Studio, by adding these cantilevers, assigning the right or the build strategy, and then really printing those parts on your machine. So then you calibrate your machine, your material, your build strategy to the simulation. You print the part, and then you cut it off from the base plate till to the this bulky area here, and then this cantilever will bend upwards, and you can measure the max SAP displacement by simply using, for example, a measurement slide or something like that. And with this max displacement, you can simply enter here. For example, you have measured 1 millimeter, and then you simply can enter here calibrate, and then the calibration will run automatically in the background. It will take about 5 minutes, so that's the reason why I do not want to start that now. But then you will end up with new inherent strain values based upon the calibration. So this is the approach that you can use when you do not have printed the part that you want to accurately print. You can also use the calibration, the cantilever, and you can find the cantilever simply in the orientation stage under tools, load cantilever, and then you can find these. I will assume to print and a minimum 4 of these cantilevers to have a more averaged result for the calibration. So far to the first part that I wanted to show, and I want to load another part here to show a new approach that we have implemented since the 2024.1 release of AM Studio. We have added the possibility of, I want to support the part in a small way here. We have added the functionality of platform removal. And what does that mean? Again, we have to define the voxel size. Probably I want to use 1 millimeter as a voxel size. And I can activate the platform removal here. But again, it's an additional license that you have to get from us to have the possibility available, and then simply start the simulation again. So again, it is getting voxeled, and the simulation is done. And now that brings me to the slider here, because this would be the results when the part is printed and still remaining on the base plate. So it's fixed on the base plate with the supports, and we can simulate the removal of the base plate. So we cut off in the simulation this constraint, and the output will be that the part will simply bend a bit to the outward direction because of the inherent strains or the inherent strains which are due to the print process inside the part. Again, part as printed on the base plate, you have zero deformation on the base plate, and as soon as you have activated the platform removal, you will get the results how the part will look like or how the part will deform when it's cut it off from the base plate. This is important for the pre-deformation, because when you want to do the pre-deformation, you have to know at which status your part will be heat treated or no heat treatment is done. Because when no heat treatment is done, the pre-deformation state which you have to use for the pre-deformation is the part removed state. If the heat treatment, for example, is done with part remaining on the base plate, then you can also use the part finished step, because then the heat, due to the heat treatment, the stresses which are inside the part are relieved. It's heat treatment or a stress relief. And so when you cut the part off, it will be accurate enough. So this bending will not longer take place. And this is a new functionality that we have implemented into the 2024.1 version. And as Daniel mentioned before, it's only a subset that we have implemented here in AM Studio directly, with the advantage of do not having to import and export always the parts between AM Studio and a simulation tool, or especially with SimUFACT additive. But if the simulation that we offer to our customer is not accurate enough, we have the possibility over the additive suite approach. You can load the projects which you have done in AM Studio directly in SimUFACT, and therefore we can use the Nexus connectivity. And I simply want to store this project here in Nexus, so I want to call it webcast or something like that. Simply hitting on create. Then I create a new Nexus project, which will be uploaded into Nexus. I can push the changes and Nexus. I will go over to my Nexus portal, my projects. And you can see here is the project webcast, which I have now stored here. And the nice thing is that you can visualize here as well the results in this whiteboard. You get all the data. I did not have assigned a material to the project so far, but yeah, you can visualize them here in the browser, or you can directly import the results in SimUFACT additive. Not the result, the data preparation, so the part with the supports can be directly implemented in or loaded in SimUFACT additive. And this is a very very big advantage of the Nexus connectivity, that both products are Nexus connected. And so you can share projects in a very easy approach between the different products in a very efficient way. So now I'm loading the part or the project, and what you can see here is the part. The supports are positioned underneath, and you can see as well the machine that I have chosen. There are some things which are missing, as I mentioned beforehand. The material. I have to configure the support removal. I have no connection, sorry about that. And the voxel size, and then I can simply run as well the simulation directly in the full version of SimUFACT. Yeah, that's more or less it from my side in a very quick and short overview.
Yeah, thank you, Peter, for this amazing presentation of how SimUFACT is working in EM Studio. So, valued audience, if you have further questions, just get in contact with me later or in the next weeks. We can give you some dedicated presentations on your part or simulations on your part. I think there is one question left what we should answer for you, Peter. So on the simulation calibration, what about the other dimensions of the printed part, like length, height, or thickness?
I'm not sure if the calibration bar is mentioned here. So the length of the calibration of the cantilever. The cantilever more or less is a standardized part which can be used for calibrating the part. So I'm not sure if this is the question or this answers the question. It's a standardized part that SimUFACT additive in this case offers to us in EM Studio for doing a very accurate calibration of the simulation and the real printing results on the other hand. So there's no need of the length and the width of the part. The only input which is necessary is the bending of this cantilever, which has to be measured. Yeah, and with that approach, you can get a very accurate deformation field out of it.
Mm-hmm. Okay, so there are no more questions in the queue. Maybe someone like to ask, then it's now time to write it into the chat. Otherwise, we like to say thank you for your attention and feel free to get in touch with us. We're happy talking to you all these topics of additive manufacturing. Now this series of 3 webinars is over. Feel free to rewatch the other ones and discuss with us or ask for demo licenses to address your needs with the easy to use and powerful software for powder bed fusion printing. So thanks from my side and see you soon in the real life.
Thank you. Bye.